Well, so we've actually skipped assignment 70, and in assignment 70 was Newton's method for finding x-intercepts. And while we're not going to actually do it, I just want you to say that, like, imagine you have a polynomial and it's got an x-intercept somewhere. And so what Newton did was to say, well, here's the thing. I could build a tangent line somewhere and find the x-intercept of that tangent line. And then I could use that x value, and I could find that tangent line at that point and find the x-intercept. And I could find the tangent line at that point. And he could get closer and closer and closer to the actual x-intercept just by repeating this process over and over and over. And let's put this in context. This is the late 1600s when he's coming up with this. Just want to say, it's very interesting and generally successful. There are some situations where either you find the x-intercept or you don't. For example, if I have something like this, did I just draw it right? Yeah. So gets an x-intercept, comes down here, gets an x-intercept, goes up there, and sometimes you just go in a big circle and you never find the one you want. But most of the time, wow, it's really, really works. It's very labor intensive without a calculator. Yeah, but remember, they didn't have streaming in in the 1600s. So let's get a move on now to assignment 71. We're talking about differentials. Not the car's differential, but here's what I'd like to have you do. Find the square root of 101. 2, or A. B, I'd like you to write the tangent line to y equals square root of x at x equals 100. And then I want you to use the tangent line to approximate square root of 101. Okay. That's what I think I'd like to work on first. So take a few minutes to, this you can do on your calculator. I think that's fabulous. You know how to write the equation of a tangent line. And then use that tangent line to get a value. Okay. Why don't you give that a go? Come back when you're done. I'll see you in a few minutes. Hey, welcome back. When I pull out my calculator and do the square root of 101, square root 101, I get the value to be some sort of error, which is unfortunate, square root 101. Okay, 10.049875. Great. So now what information do I need to write the tangent line? Well, I need a point, and the x value of that point is 100. And when I plug 100 in here, square root of 100 is 10. So I've got my ordered pair. But I also need a slope, and for us, that's going to be f prime of 100. So I've got to take the derivative of x to the 1/2, and that's going to be 1/2 x to the minus 1/2. Or 1 over 2 root x. So if I plug my 100 in there, 1 over 2 square root of 100, square root of 100 is 10. 10 times 2 is 20, so I get 1 over 20. So my tangent line, y minus 10 equals 1 over 20. x minus 100. And you could certainly distribute here, but remember what we're looking for is this, square root of 101. So if I plug a 101 in here, 101 minus 100 is 1. 1 times 1/20th is 1/20th, and then I'm going to add 10 to both sides. So I get my linear approximation, that's why I'm using L, linear approximation of the square root of 101 to be linear approximation of 101 is 10.1/20th, 0.05. Okay? And we computed this to be the actual value of the square root of 101. Now, let's take a look at this. You know, where tenths, hundredths, thousandths, 10,000ths, where 2 10,000ths apart. And for a lot of people, that's close enough. And I really couldn't do this without using my calculator. But this, I didn't need a calculator for this. And it was pretty fast. So, the tangent line near the point of tangency. Let's think about the tangent line near the point of tangency. Kind of need something a little more oomph-like. Okay. So I've got this point over here, and I'm saying that's 100, and I got a tangent line here. And what I'm doing is saying, well, I'm going to go over to 101 and say, well, you know, at the point of tangency, the tangent line and the function have the same y value, have the same slope, but nearby, they're still pretty close to each other. So I can use my tangent line to approximate function values near the point of tangency. I mean, near is an important word here because if we, go back and look at this picture, look at something like that. Sorry, I need something steeper here. There we go. Here, same. Nearby, close, but further away, not so close. So, yeah, near the point of tangency, I can get a pretty accurate estimation. Now, we won't be digging into near, and what does near mean? And if, you were in honors calc, you'd probably do that. Instead, I want to somehow connect this to this concept of differentials. So let's say this. Let y equal f of x be some differentiable function. Okay? Then the differential dx is an independent variable and the differential dy is a dependent variable depending on both x and dx. Now, the funny thing about this sentence is, you know all these words. But generally speaking, even though you know all these words, a lot of people have a great deal of difficulty understanding the implication of this statement. Okay, and so let's take a look at that implication of that statement. Let's see what it really means. So Remember this, dy dx equals f prime of x. Okay. And you know, we've always said this as dy dx equals f of x. Well, how about this? Maybe we shouldn't call it dy dx, because if I multiply both sides by the differential dx, I get dy equals f prime of x times dx. Yeah, it's not dy dx, it's dy over dx. I have a differential, I have another differential. And I would like to consider in a few minutes, what is this? What does this mean? But wait, that last sentence, the one you knew all the words from, the differential dy is a dependent variable that depends on both x and dx. That's why that statement was the way it was. Our differential dy depends on these two things: what x value we plug into f prime and what dx is. Okay? So, and now, instead of giving you a picture, I kind of actually want to do a couple differential problems. Then I'll draw the picture, and we'll talk about how the picture connects what we've been doing. Okay? But this, we're going to be doing that a lot today. So, let's go and say, find dy. This is the approximation of change in y given y equals sine 3x, x equals pi, and dx equals negative 0.02. All right? So, what am I supposed to do with all this information, Mr. Kukla? Well, remember, dy dx equals f, or in this case, y prime of x. And then if I multiply both sides by the differential dx, I get that dy is y prime times dx. So I need y prime, and here's why. What's y prime? Well, derivative of the outside, leave the inside alone, times the derivative of the inside. So our problem then looks like that. But remember, we also have this dx. Okay? So all I had to do was take that gentle derivative and plug in for my derivative here. Now I also have this bit and this bit. So let's take these and plug them in also. So I've got 3 cosine 3 pi times negative 0.02. Okay, cosine of 3 pi, that's, let's see, 0, pi, 2 pi, 3 pi. Oh, it looks like the cosine of pi, which is negative 1, times 3 is negative 3, times negative 0.02. And so I get positive 0.06 as my dy. All right? So what does that mean? Well, find dy, I found dy. Okay? And what I guess I want to show you here is, you know, when we started with derivatives, I showed you the conceptual way to understand derivative first with the limit definitions of the derivative. But then we worked on shortcuts. You know, we worked on just sort of doing the mechanical processes of derivative. Well, I kind of want to do differentials in exactly the opposite order, right? I want to say, okay, here's a thing, x squared minus xy. And I want to find dy if x equals 2 and dx equals negative 0.05. All right. So again, I know that dy equals y prime times dx. And so let's find these things, okay? And then we can just plug in like we did in the last problem. So I have to find the derivative here. And remember, this is implicit, so it's not done. I'm not done with that derivative until my derivative says dy dx equals. Okay, so what do we got? We've got 2 times the derivative of this with respect to x equals the derivative here, 2x. Yes, and I still encourage you to think about it as chain rule. Take the derivative of the outside, leave the inside alone, and then you could come back and take the derivative of the inside with respect to x. But no, I don't really need that, do I? But that helps me remember to do this. Minus, a product rule. X times the derivative of that with respect to x, and that times the derivative of that. Okay. So where do I go next? Well, okay, 2 dy dx equals 2x. Dx is 1 minus x dy dx minus, don't forget to distribute, minus y, and dx is 1. Well, I'd like to get all the dy dx stuff on one side, and that will mean plus x dy dx equals 2x. Okay, and then factor out that dy dx so that you get, I'm not bored, you get dy dx, 2 plus x equals 2x minus y. And so to get dy dx alone, I need to divide both sides by 2 plus x. So I've got 2x minus y over 2 plus x. Fabulous. I've got a dy dx. And I'm evaluating when x equals 2. I'm great. I'll be plugging 2's in here. But wait, I have a y here. So I guess not only do I have to plug in that x, but I'm also going to have to plug in a y. And I don't see a y here, which means I'm going to have to find that y first. So let's go back to this original statement up here. It says 2y equals, and I'm replacing these x's with 2's. So 2 squared minus 2y, which is 4 minus 2y. And then, move the y's to one side for y equals 4, and so y equals 1. So now I have that ordered pair, 2, 1. And I can plug in to this derivative, dy dx equals 2x minus y, 2 plus x. So I'm plugging in a 2 for the x's, I'm plugging in a 1 for the y. So 4 minus 1 is 3. Actually, the College Board really likes it when I show that plugging in, because then they know where I'm, how did I get that answer? Well, I've just evaluated at my point, and I have 3/4. So dy dx, or the slope at, that's going to be a linkage error. So let's do that and say that my derivative evaluated at the ordered pair is 3/4. But I need to find what dy is, and I know that dy dx is that derivative times dx, right? Because we were saying, look, dy dx equals f prime of x, and then we multiplied both sides by dx, and those cancel. And so derivative, not in general, but at a specific point, so I can replace that with 3/4, and dx I can replace with negative 0.05, which is negative 1 over 20. So I get negative 3 over 80 here as my dy. All right? Okay. And then the last one that I want to look at Yeah, I keep banging into that camera. Where will it end up now? Okay, so this time let's have y equals e to the sine x, where x equals pi, and dx equals 0.1. So, what do we need? Well, we need that dy dx equals, I guess we're calling this y prime, and then we're multiplying both sides by dx. And so we get that dy should be y prime times dx. Okay, so I need y prime, and the derivative of e to stuff is e to stuff times the derivative of stuff. Okay? So that's going to be e to the sine x times cosine x. But now, dx. This was just the y prime part, but don't lose that. So now I'm going to put in a 0.1 there, and for these x's, I'm going to plug in a pi. So e to the sine pi times cosine pi times 0.1. Well, the cosine of pi is -1. Sine of pi is 0. E to the 0 is 1. So I have 1 times -1 times 0.1, which gives me -0.1. Okay? I mean, I don't think these differential problems are particularly hard. I don't think the derivatives are supposed to be particularly hard at this point. Remember, we're just looking at different applications of the derivative in this chapter. And here's something else that we can do with derivatives. We can find the differential dy given, because remember, dy depends on both x and dx. We could find this differential dy. Well, what is this differential? What does it represent? And why did you have us starting with the square root of 101? Well, so we can use differentials to estimate change. Change by using the linearization of a function at a point instead of using the function itself. And so what am I talking about here? Well, linearization, think tangent line. Remember when we did the microscope worksheet? Well, if you zoom in on that curve enough, you will see that the curve looks like a linear equation. You're going to have to zoom in wicked close, but you could see that linearization of the line. Like that curve that you're working with suddenly looks, because you've zoomed so far in, like a little line segment. And we can visualize that as, oh, well, that's why the tangent line works at that point. So when I see this linearization, I'm thinking about the tangent line. And what I'm saying here then is, I could actually use the tangent line to help me estimate change in a function instead of using the actual function. Not unlike wanting to know the square root of 101, but not trying to figure out what this is. Look, here's our f of x, and I plug in a 101, and I know it's a little bigger than 10, but I don't know what that is. But instead, what did we do? We used the tangent line. So, let's think about this. Picture. And so this is some function, and I'm drawing a point of tangency here. X, in fact, kind of looks like the origin. I don't necessarily want it to be x, f of x here. And then, we're going to go over a little bit dx, delta x. And then we're going to see this. And this is our linearization, our tangent line. And we're saying that this amount here, this is dy. This is our approximate change in the value of the function as we go from here to here. Here, the dx and the delta x are the same. The delta y is actually this height here. This height is the actual change in y from x to x plus dx. Whereas dy is the approximate change in y from change in y as x goes to x plus dx. Okay, so these are the same, but these are different. Because in this situation, the actual change and our approximation of change, same amount here. But we see two different possible changes in y. We see the dy, the differential dy, which is an approximation of the change in y. It's close, but it's not the actual delta y. That's the actual change in y. And we did see these quantities. We did this on the calculator, and we came up with 10.0498 something. And that's this value. That's that. Well, I guess this was 100, 10. And no, our curve wouldn't look like this, so stop trying to make it be the same curve. And so this amount is the actual change. And the actual change as we go from 10 to 10.0498 is delta y equals 0.0498. But when we used the tangent line approximation, remember us building the tangent line at the curve and plugging in 101 into the tangent line. And so when we did that, we got dy to be 1/20th or 0.05. And we saw that, wow, this approximation was within 2/10,000ths of the actual value. And so in most cases, this dy turns out to be a reasonable approximation for the change. I mean, when we look at this is the difference between delta y, the actual change in y, and dy, our approximation of a change in y. So this distance here is 0.0002, within 2/10,000ths. This is a very small number, 0.002, unless you're a chemist. And so, yeah, that's nice. We might be able to make use of that differential. And so in this video, I just want to look at some more differential problems, but I do want to move us to that understanding of, well, how do I apply this stuff, okay? So let's think about that problem that we started class with, y equals square root of x, and we're looking for y of 101. And what I know now is that dy dx equals 1 over 2 root x. How do I know that? Well, come on, square root of x is going to be x to the 1/2, and I take the derivative, I go 1 half x to the minus 1 half, which is 1 over 2 group x. Okay, that's where that came from. Took the derivative of this given function. All right, and then I multiply both sides by dx. So going, and I get that dy is a dependent variable that depends on both what x value I plug in and my dx. So when we're thinking about this problem, square root of 101, what I'd like to do here is to say, okay, I know that this isn't the actual change in y. This is our approximate change in y that we're looking for. And I need to plug in x and dx. Now, be careful. This x, it's not 101. Okay? This x value is the x coordinate at the convenient, you'll often hear of this as referred to as the convenient or nearby point of tangency. And so the point that was nearby, the 101, that made working with this very easy, we used 100. So I'm going to plug a 100 in here. And what was that change in x value going from our nearby convenient point, 100, to the place we want to actually evaluate? So as I go from 100 to 101, I get 1. So my dx equals 1. dx equals 1, and x equals 100. So I'm going to plug a 100 in there, and I'm going to plug in 1 here. Remember again, we went from 100, the point of tangency, over to 101 because we wanted to know what the square root of 101 was. So I'm plugging in that 100, and I'm plugging in that 1. So what do I get here? Well, I get that dy equals 1 over square root of 100 is 10 times 2 is 20 times 1, or 1 over 20, or 0.05. And so, yeah, that was the approximation that I got by using the tangent line, wasn't it? Yeah, and I kind of appreciate that, that I can approximate the change in y so much easier than saying, well, how the hell do I find out what the square root of 101 is without using a calculator? And the answer is, I don't know. Then that's why, I've got this. I'm sure there are many old school ways for us to figure out the value of a function at an uncomfortable point, like square root of 101. But, in the age of the calculator, why would we care? And so I'm always looking for, if I have to do it by hand, if I want an approximation, I want it to be something that I can do quickly without even looking for the technology. Okay? Now, I notice here that my video has frozen even though the counter is continuing to tick by. So I'm going to stop the video, which means this has to be done in 2 parts, and see if, in fact, this is working. All right. When we come back in part 2, we'll do some linearization work. We'll begin some applications. Okay?